My topic of the day is how to introduce nonlinearity in activation functions. Before we move on to the video, here is the table of contents of what you will find inside the video. Neural networks. What is a neural network? A neural network is a computational learning system that uses a network of functions to understand and translate a data input of one form into a desired output. It is modeled after the human brain. It is a simplified model of biological neural system which is typically organized in layers, and it is made of numerous interconnected nodes. These nodes contain activation functions, and the patterns are predicted by feeding the inputs to the input layer, and they interact with the hidden layers where processing occurs via weighted connections. The output is found in the output layer. Single-layered perceptron versus multi-layered perceptron. Before we proceed, here is a quick difference between single-layered perceptrons and multi-layered perceptrons. A single-layered perceptron is a feed-forward network based on a threshold transfer function. It is the simplest form of an artificial neural network and can classify linearly separable cases within a binary target of 0 and 1, whereas a multi-layered perceptron is a feed-forward artificial network that generates a set of outputs from a set of inputs. An MLP is characterized by several layers of input nodes connected as a directed graph between the input and the output layers. This is a visual representation of a single-layered perceptron. Here, the inputs and the weights are multiplied into a product and sent inside a neuron. In this neuron, the multiplied products are added with other products and summed with a bias. This is fed inside an activation function which decides whether to fire the neuron or not. But on the other hand, a multi-layered perceptron is a little bit different from a single-layered perceptron. Here, the products are fed through many hidden layers and many neurons instead of just one, and they are interconnected with weighted graphs. These weighted graphs go through other activation functions, and the processing is done inside the hidden layers. After that, the output is found at the output layer. To answer this question, we can say that an activation function determines how the weighted sum of the input is transformed into an output from one node or nodes in a layer of network. It is also known as a transfer function. The main job of it is to introduce nonlinearity in the network. It calculates the weighted sum, adds bias, and decides whether to fire a neuron or not, like I explained in my previous slide. Nonlinear activation function helps model understand complexity and gives accurate results. Let's consider our neural network to be a steel pipe. In a steel pipe, if we put water in it, we will get the same water as output. This is not bad, but this sometimes does not work. If we want to put our water in different places, we cannot move the pipe because it is rigid. No matter how many layers we put in front of this, how many pipes we lay out, the answer will be the same. But instead of this, if we used a water hose, we would be able to bend it to our need. That means that an activation function makes our job more flexible. This is an example of a simple neuron. Here the input is given and we get y as the output. Multiplying it with weights and adding the bias, we get an equation like this: y is equal to mx plus c, which is the equation of a straight line. If we put another node in front of it, we will see that even after all the calculations and all the steps, we will see that we are back with the same equation that we started with. This means that no matter how many layers you put, the result will be the same, like I explained in my previous slide. So why can't we do without activating functions? Without activation functions, our output will be just a simple linear function like I explained in the previous slide. The linear function is just a polynomial of 1 degree, and they're limited in their capacity and are less effective in learning complex mapping models. Neural networks without activation function would just be a linear regression model, and they don't work well in most of the cases, and they have very limited power to calculate complex examples. Without neural networks, we would not be able to make our models learn complex data like images, video, and speech, etc. For this, many different types of activation functions were introduced. The most popular one are sigmoid, tanh, ReLU. So having a linear function makes no sense when it comes to solving non-linear functions. It can also not solve the XOR problem. If we compare this equation that I showed before to our XOR problem, we will see that W transpose into X plus bias is the same as this. And now if you put it inside a sigmoid function, let's see what happens. A sigmoid function is equal to 1 by 1 plus e to the power minus z. If we find the first derivative of it, we will see that after many steps of calculations, we find the same function that we started with. But how does the linearity disappear? We see that we have another element, which is a polynomial term. This polynomial term helps eliminate the linearity in the function and introduces non-linearity in this, which helps solve many other complex non-linear problems. If we do the same with the tanh activation function, after calculations, we will see that the sigmoid function is returning. Lastly, after adding these up, we see that the tanh function is nothing but twice the product of a smoothed curve of a sigmoid function. Finally, why do we need to introduce nonlinearity in activation functions? Nonlinear functions are those which have a degree of more than 1 and they have a curvature when we plot them. Now, we need a neural network model to learn and represent almost anything and any arbitrary complex function that maps inputs to outputs. Neural networks are considered universal function approximators. This means that they can compute and learn any function. Practically, any process we can think of can be represented as a functional computation in neural networks. Hence, it all comes down to this. We need to apply an activation function f of x so as to make the network more powerful. Add the ability for it to learn some data more complex and more complicated in form, represent nonlinear complex arbitrary functional mappings between inputs and outputs. Hence, using a nonlinear activation, we were able to generate a nonlinear mapping from input to output. Also, another important feature of an activation function is that it should be differentiable. We need it to be this way because to perform backpropagation optimization strategy. While propagating backward in the network to compute gradients of error or loss with respect to the weights and therefore optimize weights using gradient descent or any other optimization technique to reduce the error. Apart from this, nonlinear activation functions are also used in calculating radial basis functions. With this, we have come to the end of the presentation. Thank you for being with me. If you have any questions, please email to the given email address.